So in this video, we're going to be talking about the Poisson's ratio, and in particular, the negative Poisson's ratio, and also how to fabricate a foam with a negative Poisson's ratio, also known as an acidic foam. So let's start with understanding the concept of what a negative or a Poisson's ratio is, and we can do that most easily through example. Here on the left are an image of two blue blocks with a force being applied to them on the horizontal axis. The top blue block is responding by thinning along the perpendicular axis, or the y-axis in this case. So let me draw an axis here. And so it's thinning along the y-axis, and this is characteristic of a material with a positive Poisson's ratio. And on the bottom here, the material is responding to the force by thickening along the perpendicular axis, and that's characteristic of a negative Poisson's ratio. We often see a material with a positive Poisson's ratio. So for example, you can think of it as like a rubber band being stretched, and along the axis perpendicular to the force, there's a thinning effect to it. Not so much, there's not a good example with a negative Poisson's ratio, and that's why we're creating this foam today. So let's get into how we're going to fabricate this foam. So we're going to start with two things: a block of polyurethane foam and a glass tube. And what we're going to do next is put this foam into the glass tube. So into it, just like that. And let me draw this glass tube again. Here's our glass tube. And we want to put the foam in such that it fills about 50 to 60% of the volume of the tube. So here's our foam compressed inside this tube, and it fills about 50 to 60% volume. Now our next step is to put this tube with the foam inside it inside an oven. Here's our oven, and this oven is going to have a temperature of 200 degrees Celsius. And we're going to put our sample in for 25 minutes. So we're heating it, heat 25 minutes. And what's going on in this step is the rearrangement is occurring inside the foam. So the foam is in a compressed state right now, and by heating it at this temperature, we're letting the foam change its structure to stay into this compressed kind of state. So after you heat it for 25 minutes, you're going to take it out and let it cool. Gonna let it cool while still inside the glass tube for 30 minutes. 30 minutes. And this gives it the foam time to set after being heated like that. And after 30 minutes, you're basically done, and you can take the foam out of the tube and you'll have your auxetic foam. And we can look at an example of what the foam will look like in this clip right now. So let's now examine what's happening inside the foam as we're cooking it, and what kind of structural changes are taking place. So here in this image, we have our polyurethane foam without any changes made to it. And you can see spaces like here, this bubble, very circular, and then you have our auxetic foam, which is the one over here with the more jagged edges, which create unit cells that can be approximated by the reentrant shapes shown on the right and the bottom, producing a negative bulk Poisson's ratio when combined with many other cells. So let's end by talking about some applications of a negative Poisson's ratio. Polymer foams with negative Poisson's ratios have been investigated for a range of applications towards energy dissipation or redirection. The reason for this is when an auxetic foam material is compressed, it responds by becoming denser, as we mentioned before. So the result is, rather than dissipating energy to other areas of a solid, the auxetic material causes the energy density to increase. And looking at researchers at Queensland University of Technology, they investigated the application of this phenomenon to cementitious composites, or cement composites. In their study, cement samples were cast into rectangular prism samples, such as the ones in the image shown here, with a thin layer of auxetic polyurethane foam on each exterior face. So these green parts of these images. These cement polyurethane samples maintain a negative Poisson's ratio of negative 0.11 even after curing. And the compressive strength and fracture patterns were compared to samples without exterior auxetic foam layers. Samples with the negative Poisson ratio's foam layer showed decreased brittleness relative to those without, and were significantly less likely to undergo undesirable fracture patterns such as delamination. Thanks for watching.